All right, so in this video, we're going to wrap up our discussion of the second derivative test. Our fourth example of the second derivative test. Well, I suppose I shouldn't say we're going to wrap it up because we'll use this in the future because we're going to soon bring all these techniques together to curve sketch. So we'll use the first derivative test when curve sketching, and also we'll have optimization after that, and we'll use the first derivative test during optimization as well. So, but let's look at example D here. So just like the first three examples, our basically first couple steps are going to be to find the first and second derivative. So let's just hop right in and find f prime. Okay, this is three terms. So we're going to use the sum difference rule to take the derivative of all three terms individually. And then, of course, we have a negative 1/6 times x squared and a 2/3 times natural log x. So we're going to be using the constant multiple rules as well, or constant multiple rule as well. But first things first, the derivative of x is just 1. Okay, and then we have negative 1/6 times the derivative of x squared, so times 2x. And then we have negative 2/3, again, that's a constant multiple, times the derivative of natural log x, which is 1 over x. Okay, let's clean that derivative up a little bit before we take the second derivative. So f prime is going to be 1 minus, okay, we have 2 over 6, so that's what, 1/3 times x. And then we have 2/3 times 1 over x. Now, I'm about to apply differentiation again. I'm going to find the second derivative. So I'm going to go ahead and write this as negative 2/3 times x to the negative 1 power. Okay? Of course, we usually will write our final solution derivatives without negative exponents, but I'm going to do that because I'm about to take the second derivative, the derivative of the derivative. So I need that in order to use the power rule. Okay? Because I suppose I could use the quotient rule, but the power rule is much quicker. Okay, so now we're going to do f double prime. F double prime. Now I guess I should kind of make some space here. F double prime of x. Okay, again we're going to use the sum difference rule and the constant multiple rule. So the derivative of the first term is 1, or sorry, the derivative of the first term 1 is 0. It's a constant, so we have 0. And then the derivative of 1/3 x, negative 1/3 is a constant multiple times the derivative of x is just 1. And then we have minus 2/3 is a constant multiple, but then we have x to the negative 1. So the power rule says we bring the negative 1 out front and multiply, and then multiply by x to the negative 1 minus 1 power, which is negative 2 power. And let's clean this second derivative up a bit. Of course, 0 goes away. Then we have negative 1/3 times 1, so we just have negative 1/3 to start with. And then we have negative 2/3 times negative 1, so that's positive 2/3. And then we have what? X to the negative 2, so that's x squared. So we have negative 1/3 plus 2 over 3x squared, and that is our second derivative. Okay, so let's see here. Let's do this. Box off our second derivative so we can easily access it when we need it. But remember, the method here to the second derivative test is to find your two derivatives, the first and the second, and then find the critical values. So we do need to set the first derivative equal to 0 and solve. So let's see. Let's see over here. Let's move over here and solve f prime equals 0. So that's going to be 1 minus 1/3 x. I am going to change the form to 2 over 3x because that's what the negative exponent does. And usually having negative exponents is a little nicer when you're solving an equation. Now, how do you solve this? Okay, well, that's a rational equation. Why is it a rational equation? Well, because we have a rational function there where it's the negative 2 over 3x. So the way the strategy for going about solving this would be to clear either all denominators or clear at least the variable. I'm going to go ahead and clear both, the denominators. There's a 3 and a 3x. So if I multiply every term by 3x, I'll clear all denominators and then not have to worry about fractions much, at least for the time being. So again, I'm going to multiply all 3 terms on the left and the right-hand side, but the right-hand side is 0. So when I multiply by 3x, I don't change anything. So I have 1 times 3x minus, okay, if I multiply by 3x, there's going to be a 3 on the top and bottom. Those cancel out, but I'll have x times giving me x squared. And then if I multiply by 3x on this third term, the 3x on the top and bottom will cancel out, leaving with just 2 equals 0. And now I've basically transformed that rational function into a quadratic function. So that's something you do in college algebra and intermediate algebra. You take this rational equation and you transform it into a quadratic equation. Of course, we'll have to check our solutions to make sure they are legitimate, because sometimes we can't introduce extraneous solutions. But this is just a pretty standard quadratic. Let's rewrite it like this, maybe in descending form. Makes it look a little more familiar. How about we multiply by -1 so we can get a positive leading coefficient? So if I multiply every term by -1, it just reverses all of the signs. And now let's see if we can factor it. If we factor it something like this, we're looking for factors of 2 that add to be -3. So I think, -2 and -1 does it. And now that we're factored, we can set, according to the zero factor theorem, we can say either x minus 2 equals 0 or x minus 1 equals 0, which give us the critical values, at least initially, x equal 2 and x equal 1. Okay, so those should be our crit values. We'll need to check them, of course, in just a sec. Okay. Now, of course, we need to make sure they're not extraneous, but no, they're not, because, okay, what I mean by extraneous is, they don't happen to make that original equation 0. No, only 0 does that, so we're good to go there. Now, are there any values for which we have differentiability issues? That is, are there any values for which the derivative right here is undefined, but the original function is defined? In other words, let's compare the domain of the derivative with the domain of the original function. Notice that clearly the derivative has that -1 exponent means you have an x on the denominator, that means the domain of that derivative is all real numbers except for 0. Okay, so 0 is a problem with your derivative. But consider the original function. 0 is not in the domain of the original function either, because the domain of the original function is positive numbers. Why is it positive numbers? Because it has a natural log in it. And the domain of that natural log function is positive numbers. So 0 is not in the domain of the derivative, but it's not in the domain of the original either. So we don't have any additional critical values. That is, there's no cusps or vertical tangent lines. Okay, we just have our 2 critical values, 1 and 2. And now we can hop right into the second derivative test, which says evaluate the second derivative. Okay, so now we're actually going to apply the second derivative test by simply evaluating f double prime at our critical values. So f double prime of 1 and f double prime of 2. And remember, we're only looking at the sign of those results. We don't really care what the exact number is. We just care about the sign. Okay, so we would have what? For f double prime of 1, we would have -1/3. Again, plugging into the red boxed off second derivative, plus 2 over 3 times 1 squared. Okay, we have -1/3 plus 2/3. Well, what's -1/3 plus 2/3? That's +1/3, which is bigger than 0. Okay, so we have a positive result. Now, what if we plug in a 2? And then we would get -1/3 plus 2 over over 3 times 2 squared. Okay, so that's negative 1/3 plus, plus what? 2 over 3 times 4, so 12. So that's 2 over 12, which is 1/6. 1/6. So 1/6 plus negative 1/3. Well, negative 1/3 is like what? 2/6. So we have negative 2/6. I'm losing track of my head. We have negative 2/6 plus 1/6 is negative 1/6. Hopefully, I did that right in my head, which is less than 0. Sometimes, it pays to write stuff down. Here, I'll jot it down. We have negative 1/3 plus, okay, we have 2 over 12, which is 1/6. Okay, but negative 1/3, negative 1/3, that is like negative 2 over 6 plus 1/6. Yeah, negative 1/6. Okay, so we get a negative result. The first one was a positive result, and the second one was a negative result. So what does the second derivative test tell us? The second derivative test says if you evaluate your critical value, using the second derivative, evaluate your critical value, and you get a positive result like we did at 1, then that is the location of a relative minimum. So our first result is that a local minimum is at, 1 comma something. And we'll have to find that y value in just a second. And again, the other part of the second derivative test is that if you evaluate the second derivative at a critical value and you get a negative result, then that critical value is the location of a local max. So there's a local maximum. Local maximum is at, what was that critical value? 2 comma something. And now all we have to do is go and find the y values. Oh, these y values are not going to be nice. Okay, because of the nature. Well, actually, the first y value will be fine when you plug a 1 in. Okay, so you plug a 1 in. Again, we're going back to the original function to find the y values. So you plug a 1 in. What you get 1 minus 1/6 times 1, so that's minus 1/6 minus 2/3 times the natural log of 1. But what's the natural log of 1? Natural log of 1 is 0. So you get 1 minus 1/6. So what's 1 minus 1/6? That's 5/6. Okay, so that wasn't bad. But I think the second one will be a little ugly. I'm about to make the parenthesis a little bigger because, okay, here, and I'll erase that, give us some more room. If you plug a 2 in, okay, what do we get? Oh, I lost my cursor. Where'd my cursor go? There it is. 2 minus 1/6 times 2 squared, so times 4, minus 2/3 times the natural log of 2. Now, don't be tempted to round the natural log of 2. That's just some irrational number. So basically, we need to leave it as that. Now, but we can simplify the other part, right? Because we have 2 minus 4 over 6. So what's 2 minus 4 over 6? Well, 4 over 6 is what, 2/3? So 2 over 3. Okay, yeah, and that'll give us a common denominator. Because we have 2 minus 4 over 6. That's 2 minus, here, I'm not going to try to do it in my head here. 2 minus 2/3 minus 2/3 natural log of 2. Plus 4 over 6 is 2/3. Okay. Well, I would probably like to write this as a single. I'm going to combine those three numbers into a single fraction. And so if I write 2, what's 2 if we get a common denominator? Well, 2 would turn into what? 6 over 3. 6 over 3 is equivalent to 2. So we can say that our y value, if we combine that, because we all have a common denominator of 3 now, So it's going to be this fraction with 3 on the denominator. And on the numerator, it's going to be 2. Well, sorry. 2 minus 4. No, sorry. 6 minus 2 is 4. So that we can combine that. It's going to be 4 minus 2 natural log of 2. So it's kind of an ugly y value, but who cares? It's just some number. But don't be tempted to round, especially on a test. Unless otherwise specified, we're always assuming that we have exact solutions. Of course, if my directions on a homework or quiz or test or whatever exam, if the directions say to round, then it's fine to punch that into your calculator and get a decimal approximation. But if there is no rounding instructions, that means we're expected to have an exact solution. Okay, so let's graph this and see what we can come up with. F of x, the original was x minus 1 over 6 x squared minus 2/3 times natural log x. Hey, it's kind of a weird function. Again, that's a function that I have no idea what it would look like. Okay, and that's kind of the point of our curve sketching section that we're going to come to in a few. We're going to get to in a little while. Is that we're going to take these functions that you probably have, and you and I both have no idea what they look like, but using calculus we can figure out a good graph by pulling together what we know about limits, what we know about the first derivative, what we know about the second derivative. Pulling all that together, we can get a nice sketch of the curve. Okay, so we said that what? We had a local minimum at 1, 5 over 6. And okay, I guess the question is, because that's 1, 5 over 6, I suppose the question is then, do we recognize that the y value is indeed correct? So it says the y value is 0.833. Is that the decimal approximation of 5 over 6? Because, again, Desmos is always going to give you decimal approximations. And, yeah, you see that is the correct decimal approximation. So, yes, our relative min was correct. Now, what about our local max? We said we have a local max at 2 comma something. Well, okay, so we did get the right location. Let's see if my y value is correct. I had to do some arithmetic to get that y value. So is the decimal approximation of our y value, is it 0.871? So let's type in 4 minus 2 natural log of 2 divided by 3. Oh, and it would probably help if I used parentheses. I didn't get the right answer because I didn't use parentheses around the numerator. Now divided by 3, yeah, 0.871. So that is the correct y value. Okay? So yeah, there you have it. We located the relative extrema with using the second derivative test. And again, why would we do this? Because let's just say for the sake of argument that we didn't care about the increasing and decreasing behavior of the function. So the first derivative test allows us to locate the relative extrema, but we first have to identify the intervals of increase or decrease, and then we observe for changes from increasing and decreasing or vice versa as we move from left to right. Okay, so that's, we build up that chart. That takes a good bit of time. If you don't care about all of the increasing and decreasing behavior, the second derivative test is probably quicker because you can quickly differentiate once, differentiate again, get the second derivative, then go back to the first derivative, find the critical values, and then plug them in real fast. We didn't have to make that big sign chart over here with all of the increasing and decreasing behavior. So in sometimes, not always, sometimes it's just quicker. This is a quicker way to find the local extrema. But remember, both the first and second derivative test are methods to find the relative extrema. Here, let's just glance real fast, just because I like to look at the graphs of derivatives. Look at the graph of the derivative. Notice that where we have a local extrema, which is at 1 and 2, notice what we have on the derivative. The derivative is green here. Here, I'll make it dashed. The green derivative has x-intercepts, that means the derivative is 0, the slope is 0, where we have our local extrema. And that's what Fermat's theorem told us way back a while ago, that if you have a local extrema, it must occur at a critical value, where the slope is either undefined or 0. And here we have two instances where the slope is 0 at 1 and 2, and those led to the local extrema on the original function of 1 and 2. Okay, let's see, second derivative. Notice how the second derivative, here let's make that dashed. The second derivative is positive until you get to, looks like square root of 2 to me. 1.1414, that's the square root of 2, right? And so yeah, if you kind of look into, like right here, look to the left of that point, the function's concave up. To the right of that point, it's concave down. And so what the second derivative test was saying was, we found a critical value 1, and where the critical value was 1, it was on a location where the function was concave up. Therefore, the second derivative was positive. We also found a critical value 2, but where the function, where 2 was on the function was also concave down, which means the second derivative test said we led to a local extrema. All right, so that's the first derivative test. We will use this again in the near future, so be careful when you're working lots of examples, because don't work a bunch of examples then forget it, because we will use this when we curve sketch and when we solve optimization problems in the very near future. As always, feel free to reach out. Please reach out if you have any questions at all. Always more than happy to help. I'll catch you in the next video.